The star Tau Ceti is 12 light-years from Earth. That number is easy to say and almost impossible to understand. Light travels at 300,000 kilometers per second. In a single second, it crosses a distance greater than the circumference of the Earth 7 times. In 1 year, it covers nearly 10 trillion kilometers. Tau Ceti is 12 of those years away, the fastest spacecraft ever built by human beings. NASA's Parker Solar Probe travels at roughly 690,000 kilometers per hour. At that speed, a journey to Tau Ceti would take approximately 19,000 years. And yet, in the film Project Hail Mary, a single astronaut makes that journey alone and arrives. The question worth asking is not whether the film is fantasy. The question is, how much of it is? Welcome to 1% More. One video. 1% more than you knew before. Project Hail Mary, based on the novel by Andy Weir and released as a film in 2026, is unusual among science fiction productions in one specific way. Its author spent years researching the physics, astronomy, and biology behind the story, consulting with scientists during production. The result is a film that, while clearly fictional in its premise, is built on a foundation of real scientific concepts that researchers today take seriously. Astrophysicist Jacqueline McCleary of Northeastern University described the film's science as self-consistent and grounded, pushing against the limits of current knowledge without breaking the rules physics has established. And the most important question the film raises is this: is the journey it depicts physically possible? Not today, but ever. The star the astronaut travels to in Project Hail Mary is not invented. Tau Ceti is a real star, located approximately 11.9 light-years from our solar system in the constellation Cetus. It is a G-type star, the same category as our Sun, slightly smaller and less luminous, but similar enough in character that it has long attracted the attention of astronomers searching for potentially habitable worlds. Tau Ceti has 5 confirmed planets. One of them, designated Tau Ceti, or orbits within what astronomers call the habitable zone, the range of distances from a star at which liquid water could theoretically exist on a planetary surface. The film calls this planet Adrian. In the real astronomical catalogue, it is simply Tau Ceti e. What is known about it is limited. Its mass is estimated at several times that of Earth. Whether it has an atmosphere or liquid water remains unconfirmed. But the planet exists. It orbits a real star at a real distance. In 1960, Tau Ceti was one of the first stars targeted by Project Ozma, the earliest systematic scientific search for signals of extraterrestrial intelligence. No signal was detected. The search has never entirely stopped. The most technically demanding aspect of Project Hail Mary, and the one that departs most significantly from current capability, is the journey itself. Reaching another star system within a human lifetime requires traveling at a minimum of roughly 10% of the speed of light. At that velocity, the journey to Tau Ceti would take approximately 120 years. To reach those speeds, conventional chemical propulsion is not merely inadequate, it is not even in the same order of magnitude. Several serious propulsion concepts have been proposed to bridge that gap. Nuclear pulse propulsion, first studied under Project Orion in the 1950s, would use controlled nuclear detonations to generate thrust, theoretically achieving up to 5% of the speed of light. The project was halted not for technical reasons, but due to the 1963 Partial Nuclear Test Ban Treaty. The Breakthrough Starshot Initiative, announced in 2016, proposed accelerating gram-scale probes to 20% of the speed of light using a ground-based laser array, enough to reach Alpha Centauri in approximately 20 years. The target is a probe, not a crewed vessel. But the underlying physics has been validated: antimatter propulsion. The concept closest to what the film imagines remains theoretical. Antimatter exists and is produced in particle accelerators. But the quantities required for interstellar propulsion are measured in tons, and the entire global production of antimatter to date amounts to a fraction of a nanogram. The obstacle to interstellar travel is not physics, it is energy. The laws of the universe permit the journey, they simply demand a price that current technology cannot pay. Among the scientific details in Project Hail Mary, one stands out for its precision. The film depicts the passage of time differently for the astronaut than for the people he leaves behind on Earth. The faster an object moves through space, the more slowly time passes for it relative to a stationary observer. This is time dilation, a direct consequence of Einstein's special theory of relativity, published in 1905. This is not speculation. It has been measured experimentally. In 1971, physicists Joseph Huffaler and Richard Keating flew extremely precise atomic clocks around the world on commercial aircraft and compared them to identical clocks left on the ground. The airborne clocks, moving faster, ran measurably slower, exactly as relativity predicted. Today, the GPS satellite system requires relativistic corrections to function accurately. The satellite's clocks run at slightly different rates than clocks on the surface. Without accounting for this, GPS positioning would accumulate errors of several kilometers per day. Relativity is not a theoretical abstraction. It is built into the infrastructure of modern life. For a spacecraft traveling at 50% of the speed of light, the effect becomes substantial. An astronaut aboard would age noticeably more slowly than people on Earth. At 90% of the speed of light, the effect becomes dramatic, years passing aboard the ship while decades pass at home. A sufficiently fast spacecraft is, in a precise and measurable sense, a time machine. In 1903, the Wright brothers flew a powered aircraft for the first time. The flight lasted 12 seconds and covered 37 meters. 66 years later, human beings walked on the moon. In 1928, Alexander Fleming identified penicillin. The technology to mass produce it did not exist for another 15 years, years during which millions died from infections that penicillin would have cured. The history of science and technology is, in part, a history of the gap between theoretical possibility and practical capability. Physics identifies what is permitted. Engineering determines what is achievable. And the distance between those two things has, consistently, proven to be a matter of time, not impossibility. The journey depicted in Project Hail Mary does not violate any known law of physics. Time dilation is real. Antimatter propulsion is theoretically viable. Tau Ceti exists. What the film imagines is not impossible. It is, by the current state of human engineering, unreachable. Those are different things. The gap between where we are and where the film begins is enormous. But the direction is the same. Tau Ceti is in the sky tonight. From the southern hemisphere on a clear night, it is just barely visible to the naked eye, a faint point of light in the constellation Cetus, indistinguishable from the thousands of other stars around it. It has been there for 10 billion years, longer than our sun, long enough that, if life exists around it, it has had more time to develop than life on Earth has had. We do not know if anything orbits Tau Ceti that would recognize another living thing. We do not know if, in some distant future, a human being will make the journey the film imagines. What is known is that the physics permits it, that the star is real, that the questions the film is asking about distance, about time, about what lies beyond our solar system are questions that working scientists are genuinely trying to answer. Science fiction, at its best, does not predict the future. It maps the territory between what is known and what is possible. And that territory, it turns out, is very large.